Sec.
Your screen behaving all fine?
Yeah, it's just I think before I couldn't hear you, but now I can. I think my volume on my laptop was down. Is that better?
Yeah, it's all fine on my
Brilliant.
side.
Okay. Excellent.
Okay, Kevin. Well, thank you very much for agreeing to give a talk to the radar group here at UCL. Professor Kevin Chetty is going to speak on real-time short-range sensing using 60 gigahertz millimeter wave radars. And I look forward to your talk, Kevin. Over to you.
Thanks, Matt. Okay, so yeah, thanks for joining. My name is Professor Kevin Chetty, and I'm based here in the UCL in the Department of Security and Crime Science. And I'm going to talk about some work which my colleagues Paul Brennan, Lai Ban Lok, and Fangzhan Shi have been doing on real-time short-range sensing using 60 gigahertz millimeter wave radars. Just one point before I start. I gave this talk recently at the MSIG symposium. So if any of you were there, apologies. You know there might be some repetitiveness, but hopefully it'll still be useful. Okay, so in this presentation, I'm going to go through two radar projects which we've been working on. So it's kind of in two parts. The first is a 60 gigahertz FMCW radar, and the second is a 60 gigahertz CW radar, Doppler radar. And for each of these, well, I'm going to first introduce kind of millimeter wave technology, kind of more broadly, and then talk about for each, the usual motivations, the architectures, some testing that we've done, and results and analysis, and then kind of where we're going in the future with it. I suppose the two headline kind of takeaways from the presentation is that for part one, the FMCW radar, our objective is to widen the accessibility to radar technology. And we've done this by developing a radar which we call the DreamHAT radar for the Raspberry Pi. So I'll talk about that in more detail. And for part two, our objective is really to move towards real-time human activity classification in remote patient monitoring systems, or RPMs, through the integration of embedded machine learning or edge processing. So this slide just kind of shows some benefits of millimeter wave radar, and I suppose the benefits, they kind of apply. A few of these points apply more broadly and generally to radar systems themselves. And I know I'm talking to a group of radar engineers, so I won't kind of labor these points, labor on these points too long. But I think some points I want to highlight are compact antennas. So the short wavelengths of millimeter wave radar allows us to have compact antennas, which can then be integrated into small devices. And I think that as millimeter wave technology becomes more accessible, cheaper, and kind of smaller, it's going to start to kind of overtake or complement kind of the more traditional sensors like optical and acoustic, and I think having these kind of antennas in package on the chips will kind of facilitate new applications in robotics, healthcare, security, and so on. The second point I wanted to talk about was, or just mention, was I think we're seeing a democratization of millimeter wave technology now, and it's becoming increasingly accessible and affordable. And a lot of that is being driven by its use in other industries, such as the automobile industry, where they're developing kind of self-driving cars and automatic parking, etc. Final point here is that I think with millimeter wave technology, sometimes the penetration capability gets a bit oversold. So it can, penetrate through materials, especially for the lower millimeter waves, like 24 gigahertz. But I think, for those of you who know my previous work in passive Wi-Fi radar, when we were doing through-wall passive Wi-Fi, we were detecting targets at 10 meters standoffs through double cavity thick walls, and that worked quite well. Whereas that's just not really possible with that type of capability is not really possible with millimeter wave radar, though it does have some penetrative capabilities. So here are just some kind of examples of commercial millimeter wave systems on the market. Which you can see on the top left, is the a kind of a single chip millimeter wave radar system from Texas Instruments. And I think quite a lot of you are quite familiar with this system, and we really like it because it allows us to access the raw data, directly from the board. B is another one from Texas Instruments, which has 4 antennas, so it kind of gives good azimuth resolution. C is a radar chip, millimeter wave radar chip from Via, who are a Israeli company, and this chip is equipped with 20 transmit and 20 receive antennas, so it's got kind of full spatial coverage. But when I last checked, it was quite expensive. It was around $3,500 USD, and I think we've had some issues with it, just kind of trying to pull off the raw data from the system. D is a automotive 4D automotive imaging radar, but this only outputs the point cloud and doesn't give you access to the raw data. And E and F are kind of single millimeter wave radar chips with antennas in package, so they've got the antennas built in, and I'll be talking about E and the Infineon chip in a bit more detail. But I think the point here is that some of the issues that we've encountered with these existing commercial systems are that, one, there's quite a steep learning curve to get going with some of these systems. I think especially for new PhD students and master's project students, that learning curve just adds a bit of a barrier to entry, and kind of inhibits. It takes a while to kind of get going with them. The other issue is that a lot of, not all, but some of these systems are quite closed, and you can't get access to the raw radar data. And I think, with more people being interested in machine learning and AI and classification, with kind of using those approaches, that doesn't really help, because we really want access to the raw data. And even some of these systems, they you have to use the kind of, on these platforms, you have to use the manufacturer's proprietary software, which again can limit what you can do. So based on kind of some of these issues, we built the DreamHAT radar, and this is a plug and play 60 gigahertz millimeter FMCW radar hat for the Raspberry Pi. For those of you who don't know, or are not familiar with kind of Raspberry Pi terminology, a hat stands for hardware attached on top. So what we've built is a board that can kind of sit on top of a Raspberry Pi and act as a radar. So I'll kind of come back to it in a second, but some of our motivations for this project was, as I mentioned, we wanted to increase the accessibility of millimeter wave radar technology to a wider audience. So not just PhDs and researchers, which we think that's an important kind of class of people using it, but also out there are a lot of kind of really technically gifted electronics hobbyists and tinkerers, people who are interested in IoT, software developers. And we think kind of there's a group here that if they had access and easy access to radar technology, they could probably do some cool things with it and interesting work with it. So that was kind of one of our motivations. And the other thing was the kind of education piece. Rather than younger people, experiencing and coming into contact with radar systems when they maybe start university and computer science or electronic engineering degree, maybe kind of earlier than that, if it was, there are a lot of kind of young people into Raspberry Pi, so maybe there was a scope for to access those students. In terms of requirements, we wanted this radar to really be plug and play and easy to use. So the idea was, once you get it out of the box, you can get up and running within about 15 to 20 minutes. And also to have some ready to go examples. And the idea here was that before you even start to kind of play around with it or start coding in it, you can just, put the image file on, click the icon on the front, and you've got some examples ready to go. And real-time kind of visualizations, so you can see what the radar, have some insight into what the radar can do. And then when you're ready to get going, you already have some example code to kind of jump off from and start working on it. And then it was also important for us for this system to be open, so enabling full access to the raw radar data. To make sure that the design, schematics, the processing code were all accessible and open. And then our hope was that this would then provide an opportunity to build up a community around some of this type of radar hardware, and allow this community of users to build upon and help improve the hardware and software, kind of all together. So we chose the Raspberry Pi because it's quite recognizable. A lot of people know what it is and have experience using it. So it's a good platform. It also has a large user base and global community already. So I read that since it kind of launched in 2012, there have been 68 million units sold worldwide. And then if you actually look at the demographic of these users, initially a lot of the users were kind of hobbyists and tinkerers. And the article I read was that a lot of these younger people who are hobbyists and tinkerers end up kind of getting jobs in industry, whether it was kind of tech or defense, or automotive vehicles or whatever, but they brought the Raspberry Pi with them. And actually, over the last few years, we're seeing a big user base in industry as well. It's quite affordable and widely available, so typically around £100, but obviously depends on what model you get. And then the Raspberry Pi, the community really like this idea of hats, the hardware attached on top, which offers plug and play compatibility for a range of boards. For its the Raspberry Pi's GPIO. So here's a few examples of the AI hat, the Sense hat, and the thermal camera hat. And I like the Sense hat because it has an accelerometer on it, a magnetometer, temperature sensor, barometric pressure sensor, and it can detect kind of when it's light or dark. So it's got quite a few sensors on it. And also with these hats, you can stack them, so you can integrate numerous sensors onto a board. The boards are quite portable and low power, and there's also solutions for embedded applications, which is something we're quite interested in looking at in the future. So this is the Infineon chip that we use to build the radar breakout board. It has a 60 gigahertz operational frequency, and it transmits both up and down swept frequency chirp waveforms, or FMCW waves. It has a 5.5 gigahertz bandwidth, so that range resolution of around 3 centimeters gives some nice kind of spatial, you can detect targets quite well spatially. And it has a 5 milliwatt output power. And this diagram just shows, so you can see it has 4 integrated antennas built into the chip. And actually from the image here, you can see the 4 antennas on the chip. But the antennas have a gain of 3.5 dBi and a beam width of 35 degrees and 65 degrees in the H plane and E plane respectively. And even if you look at the dimensions, you can see it's a tiny chip and can fit on the fit on your fingertip. So just running some basic numbers from our dusting off the old radar theory books. We usually run 1, 2, 4 samples per chirp. So putting it, kind of churning through the numbers, we see that gives us a maximum unambiguous range of the radar of 15 meters. And given that the phase difference between adjacent antennas is pi sine theta, our strategy for location is to identify the amplitudes and angles of the largest targets in each range bin with thresholding, which allows detection of multiple targets over the 15 millimeter range of the radar. So this is the radar breakout board, which we've built around the Infineon chip for the Raspberry Pi. And we've built it to the Raspberry Pi Hat Plus specifications, which allows us to call it the DreamHAT Plus. And because we built to the specifications, we also got approval from Raspberry Pi to be an official powered by Raspberry Pi product, so we can use that logo, and our future boards will kind of have that logo. So yeah, this is the board, and this diagram. Sorry, it's quite small text. Sorry, it's hard if it's hard to read. But it just shows the kind of a flow diagram of the signal and data processing flow. And I won't go into it in too much detail, but there's kind of 4 key modules, or 4 key modules. So there's the range Doppler processing, which includes MTI processing. Then there's the digital beamforming. Then there's the range angle processing, and then finally target detection. I think I'll redo this slide at some point just to make it a bit clearer. And as I mentioned, we we're kind of, our goal is to be open source and have everything kind of available for users. So on our website, we have, we kind of put all the information. So this is the physical specifications and the footprint. We also kind of publish and kind of make available the PCB schematics. And if you look lower in this diagram, you see drawn by LBL, which is Liban. So Liban, who we work with on this project, is kind of, that's he's done a really good job in designing that PCB around that. I also said we built, we provide some built-in examples when you kind of, so once you, to get people up and running with the radar. So this example is the example one, which sometimes it takes a while to load. Just give me a second. Sorry. Yeah. Okay. So it shows the DreamHAT, me sitting down on a chair, and you can see the stationary target response, and then I just kind of rock back and forward, and you can see the response kind of going from positive to negative Doppler, and then I get a bit faster. Next, it's my hand. And when my body was rocking, you could see different components from my head and my knees. And now I'm kind of going hand and body in kind of asynchronously, and you can see that. And then finally, we've got two hands going back and forth, and you can see the response in that range Doppler plot. So that's one of the examples that we provide with the DreamHAT. The second one, again, it's the range Doppler again, but in this case, it's Liban walking backwards and forwards, and you can see the response in again in the positive and negative Doppler sections of the range Doppler plot. So that's kind of the range Doppler output, and the code we provide for that. The second example is tracking on an XY map. And what I thought I'd do here is just quickly show the interface first, just so you understand what's going on. So at the top, you see the location of the DreamHAT. And then when there's a target detection, it gets shown as a yellow marker. But then over time, that yellow marker fades away and changes color, which allows that kind of detection to see the detections over a kind of a temporal trace, or a kind of like a track. So here's an example two of me just walking in a circular motion around a room, and you can see the detections and the kind of temporal trace of that motion. Next is another example. This is Liban walking around a room in a kind of random fashion, and again you can see the DreamHAT detecting, with its detections and then fading out over time. So it works quite well there. The other thing that I didn't mention about the range Doppler plot was the example I showed was only for one person walking, but we've done a few experiments, and it does, when we have multiple people walking around a room, you can see responses from multiple people. So that's another example which we need to kind of optimize and build in. What I thought I'd show now is just a few examples of how other people are using the DreamHAT. So here's an example of a research group in, I think, Northumberland, who have put the DreamHAT on a drone. They're planning to take it out to Antarctica at some point, and so they were just kind of doing some initial testing, kind of flying around with the DreamHAT on a drone. The next example is quite a nice example. So this is where I was talking about having kind of tinkerers and electronics hobbyists and enthusiasts and build projects. So this guy is a YouTuber called Rob Smith, and he's quite a popular YouTuber who does a lot of electronics projects, and he's built if you remember, I don't know if anyone's seen the iconic Aliens movie from the 1980s, where he's built the motion detector from that movie using the DreamHAT. And what's nice about that is, one, in the past, a lot of people have tried to build replicas of this, but they've just had a video showing the output here. But this one actually works, and it works quite nicely. And you can see, I don't know if you have sound, but you can see him testing it out. So yeah, so I'll let it finish. And he's got the T-shirt from the Aliens as well. But anyway, so what's really nice about this project, as well as it being kind of, aligned to popular culture or whatever, what this guy Rob has done, made some nice improvements to the code to make it more efficient and just run faster. But he's also incorporated into that handheld device an accelerometer, and he spent quite a lot of time trying to crack the code for that. But it now works with an accelerometer, so it compensates for the motion of the DreamHAT. So you can kind of point that motion detector in different directions. But what I really like about this is that by kind of allowing people to develop their own projects, you can get lots of different improvements in different areas of the tech, and to help it be used for different applications. And then he built this in line with the recent launch of the Alien Earth show. Another few examples. Matthew Ash and James Brown, who are ex-UCL PhDs in the radar group. I think most of you know them. They have a startup now called SuperSense Technologies, which focuses on dementia and kind of in-home remote patient monitoring. But one of the things that they did, they used the DreamHAT, and it was a shopping mall in Cambridge. They used they set up a plinth, and it with a busyness meter, and there's quite a kind of nice funny video here of this kid running in front of the busyness meter, and just you can see the dial going up. So it's just another nice use of the DreamHAT. And then finally, this company Perceive AI, who are based in the Netherlands, near Delft, I think. They do a lot of work on autonomous vehicles and self-driving cars and motion, kind of moving platforms. But I think they're building some kind of gesture recognition capability for inside cars. And I won't show the video here, but there's a LinkedIn post from Perceive AI from yesterday, and they just show them using it. They've built their own interface, and they can detect gestures of someone moving their hand clockwise or anti-clockwise, and they're kind of building on that. So just another nice use of the DreamHAT for radar applications. So that's the end of part one. That's kind of linked to our website. So if you kind of want any more technical information about the DreamHAT radar, then you can go there. One thing I did forget to mention when I showed the breakout point is that the Infineon chip communicates with the Raspberry Pi via SPI. So and it gives you that SPI kind of connection gives you full control of the radar. So you can kind of change the waveform parameters and a range of other operational parameters of the radar. So part two of this presentation, as I said, I'm going to focus on the 60 gigahertz continuous wave radar, which we've built. And the motivation around this is a lot to do with kind of the aging population. And so this is for a healthcare application. And given that the aging population is putting quite a lot of stress on healthcare systems, it's really driving the need to remotely manage patient care, to rapidly identify worsening chronic conditions. And a lot of the people we speak to in this space kind of talk about prevention rather than cure. So being able to monitor people in their homes unintrusively as a way of kind of helping it and supporting that stress on healthcare systems. And remote patient monitoring technologies have received had a lot of attractive, a lot of people have been interested in these over the last few years because of their ability to monitor patients at home over long periods. So doing things like learning their pattern of lives, detecting vital signs such as heart rate and respiration, and it can even things like early identification of factors that can lead to the onset of disease. So identify normal gaits. For example, in Parkinson's disease, you get this freeze of gait kind of characteristic, which if you were to detect early on, you could kind of intervene better. And also things for like fall detection, which is a leading cause of hospital admissions globally. And the idea of these being able to promote independence, safety and well-being and reduce hospital visits. So that's kind of a big motivation for these remote patient monitoring technologies. And in this space, video cameras and wearables represent the state of the art. Video cameras are quite accurate, but sometimes are criticized as being too invasive. They're also limited by light conditions and can have a restricted field of view, and also require purpose-built infrastructure. Wearables, on the other hand, are also quite accurate, but they suffer the high risk of non-compliance, especially amongst the elderly who either don't like wearing them or forget to wear them. Whereas radar technology offers a nice solution here, because it can be a robust and reliable solution to detect people uncooperatively over long periods, and it's quite privacy preserving, so it doesn't produce images of a person or identify them as an individual. It can be used in numerous environmental settings, and with recent advances in machine learning, it's also kind of enabling applications in human activity recognition. But some current issues around remote patient monitoring systems is that they rely on cloud-based infrastructures, and a lot of that is because they send data to the cloud to do some complex data processing for large machine learning models, and this can be quite expensive. It can introduce latency into the system and open up risks to data privacy. So a solution here is to use embedded machine learning, but the challenge obviously is to be able to do machine learning on these resource-constrained devices. But some of the benefits are that you can preserve privacy by keeping all the data on site and on the device. You can reduce network dependency, and you can address latency by enabling kind of real-time responses, particularly in RPM system, which sometimes they're critical life-threatening events. So this is the 60 gigahertz Doppler radar which we built. This one is again built around an Infineon chip, but it's slightly different to the previous one which we used for the DreamHAT. So this is a continuous wave radar, millimeter wave radar, with two integrated antennas on the package, and you can see them kind of from this image. And here is the circuit diagram. So the processing we use for this system is that the raw signals undergo Doppler processing to extract velocity and amplitude. So this graph shows for a person walking the measured Doppler detections, which are in a blue trace, and then in orange the amplitude of those detections. So the radar is equipped with an 80 mega 328 microcontroller, and that is that's the kind of the idea is to ensure kind of light operation under the tight resource constraints. And so we process the data on that chip using a quantized LSTM model, and supported by TensorFlow Lite for microcontrollers. So in terms of the processing, the measurements that from the radar are screened for invalid samples and then normalized between -1 and 1 using an empirically derived mean and standard deviation. And then we segment the data into 50 millisecond windows, which are at 25 samples at 50 hertz. And then that window represents a short temporal snapshot, which we then use for activity classification. So this is the quantized LSTM model, and it consists of 32 hidden units, followed by a small fully connected layer for the final predictions. In the post-training quantization, we convert both the weights and activations to 8-bit integers, which significantly reduces the overall model size. And then the internal states of the LSTM are reinitialized at each inference cycle, which helps prevent gradual drift. And then lastly, we use the microcontroller's hardware multiplier and pre-computed lookup tables to perform efficient matrix multiplication routines. So you can see the diagram here of kind of the pipeline of that LSTM. And then from this achieves an inference latency of 300 microseconds per 15 millisecond window. So we tested this out, kind of underwent a campaign of experimental trials, which involved 4 test subjects undergoing various activities shown here. So walking, irregular walking, standing, painful standing, and falling. And so those 4 test subjects performed a variety of these activities in front of the radar, and we kind of in the end had a data set of 500 500 kind of activities with 500 label samples per activity. So so a lot of kind of just testing of doing these activities in front of the radar. And then to train the model, we used an 80-10 train test split. So the results are shown here, and the radar, the CW radar was evaluated in 3 primary metrics: precision, recall, and accuracy. You can see that the results are quite good across the board, with falling being the best performing kind of activity, and I think irregular walking being the worst. As mentioned, we kind of, so we evaluated the accuracy and the latency as well, and the latency, as mentioned, was 30 microseconds for each 15 millisecond window, and that was supported by a confidence aggregation mechanism, which is able to aggregate predictions over multiple frames to just increase their statistical confidence. I haven't really gone into any detail on that there, but we recently presented a paper at the SPIE conference, and that's detailed there. So just to summarize the part 2 of this talk, UCL's remote patient monitoring system is basically developed around the 60 gigahertz low-cost Doppler radar. It has in our tests, it has quite high classification accuracy in the 90s, and it was kind of worked best for fall detection, and that it used a quantized LSTM model to facilitate on-device machine learning. So it operates in real time with an inference latency of around 300 microseconds per 50 millisecond window, and it's supported by that global confidence mechanism. So that's it for the presentation. I don't know how I was for time. And just finally, just to thank all the kind of people that work on this project, which is Paul Brennan, Lai Ban Luck, Fang Zhanxi, and Chong Tan. Thank you very much.